Why would the Copernican principle be sacrosanct? That's what I mean.
Well, we're getting into philosophical issues here, which make me uncomfortable. I'm a physicist, so I try to stick with what I observe half the time. The other half of the time, when I'm publishing papers, I have to stick with the scientific principle. I solve my equations, I try to fit the data. But then I run into this problem with the Copernican principle. So then I go around privately worrying about that, and I speak to my colleagues and they're not happy about it. I gave a talk at the Primmer Institute 2 weeks ago and stressed this, and other cosmologists agree with this. I've seen a lot of publications are coming out. We're not able at present to tell you whether we're in a special place in time or space, observationally. We can't even tell this the case. When I published this paper in 1992, I was the first to do this kind of model, phenomenologically. People ridiculed me at the University of Toronto, the astronomy department. Not anymore. There are many papers that have been published the last 2 or 3 years trying to suggest ways to prove yes or no whether we violate this principle. It's become a serious issue. I was ahead of my time, if I may say so. And you don't want to be that by the way, physician.
Professor Moffat, you described the big bounds in an eternal universe. Could that big bounce where the time was negative on one side and positive on the other side, could that be a point of minimum entropy or maximum order, so that it's an oscillating bounce from minimum to maximum entropy?
That's exactly what it is. Because at t equal to 0, the seagull wings. By the way, where the point where the seagull wings hit the scale factor a of 0 at t equals 0 is positive. This is the point. So this is why you don't get a singularity. It's a smooth. It's not a kink. Smooth. So there, the entropy is at a minimum, and the universe is in a very ordered state, minimal entropy state. So when you go away from the beginning, t equal to 0, the entropy increases. And this is precisely, I like this. It fits. This is the way the universe would look, in my opinion.
So this maximum order would contain, what would maximum order be, minimum entropy? All of the knowledge of the universe, or universes?
Well, it's called the heat death. The entropy keeps increasing, the universe becomes completely ordered. Heat cannot produce work. And it's a bad situation. I don't want to be there when it happens. I'm sure I won't be.
The other question I have related to the baryonic oscillations. These would be probably oscillating over a whole range of frequencies and might have information, perhaps, that would dictate how our chemistry manifests, for example.
Let's see. Well, this is to do with cosmology, so what it's saying is that where the trough of the oscillation occurs, we get a void. You will see a void in the distribution of galaxies. And we do see these voids, many of them. So in a sense, I already know I'm right. I get my $10, okay? But the chemistry, the standard, the particle physics still works. We're talking about the distribution of galaxies at a very large scale.
What I'm wondering is if that maximum order at that bounce point maybe dictates is there a residual effect of that in the universe that dictates?
No, because at the
order?
beginning you just have radiation, light, and you have quarks and leptons. It depends where you, at the beginning of the universe, it's, you have very high density in this 10 to the 15 grams per cubic centimeter, but not quantum gravity.
But your fifth force, could that be in any way related to the other dimensions of string theory?
No. Well, you can get anything you want out of string theory at present. Yes.
Okay, thanks.
You mentioned you published 100 data sets that match the model. Have you run across any that haven't? And secondly, would your model predict the observation of a collision of a star and a black hole off that?
To answer the first question, yeah, there are data which don't fit so well, and there better be, otherwise people think I'm cheating. Okay? Because you can't get perfect data. These are complicated astronomical observations. So there are obviously galaxies which have some discrepancies in the prediction, but I believe my prediction. But then I'm biased, okay?
Hi. My understanding was that gravity, Einsteinian gravity, was one of four forces that differ in the range in which they have maximum effect. So nuclear force, for example, short range, and so on. So is your theory equivalent to formulating the problem as an additional force which is of longer range than the gravity, but otherwise the gravity being the same?
A good question. If you translate Einstein's geometrical picture into a force, which you could do, then it's a long-range force. It's called long range. It reaches to infinity because the graviton is massless. It has no mass. The graviton is the particle that makes up, supposedly, produces the gravitational force, like the photon produces the electromagnetic force. And the photon is massless, it's a long-range force. Electromagnetism goes all the way to infinity, so to speak, and so does gravity. Whereas my so-called fifth force, this vector field, phi mu, has a mass. This is very important. If it doesn't, the theory doesn't work. So it has a range. Beyond that range, the fifth force disappears, and you get by Einstein and Newton.
Okay, thanks.
Do you think that with your theory, this could help experimental physicists at the LHC to put together an experiment to definitely prove that there is no such thing as that matter?
Well, as you heard, you read in the newspapers, CNN breaking news. See, 3 days ago, they got collisions at the LHC, which is amazing. Okay? It's a 450 GeV, but 450 billion electron volts. But they're going up to 3.5 billion electron volts, hopefully by Christmas or early next year. So they're looking for dark matter particles. This is one of the big things they're looking for. They're also looking for the Higgs particle. And the problem is, if they find a particle which can be the dark matter particle, they have to prove that it's stable. The electron and proton are stable particles, so they make up matter. And you can't make up dark matter without a stable particle. And this is very difficult to prove. You have to do this cosmologically. So the whole thing is a difficult problem. What they've done is, that experiment's $10 billion, which is over 14 years. It sounds like a lot of money, but